Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Thea Faridani with us today. Hello, Thea.
Hi, Frank.
It is December 8th, Friday, as we record this. And I think we're both on the west coast of the US. Where are you located at, Thea?
I'm at UCLA right now.
UCLA. I won't ask if there's any snow in LA. Just like there's no snow in Phoenix.
Well, it snowed for about 30 seconds last year. It was a
Whoa!
whole hullabaloo.
Woo! Did you get out and make a snowball?
No time.
I think the last time it snowed in Phoenix was like 1985 or something, and we got like a tenth of an inch or something like that. It was pretty
Oh, delightful.
yeah, yeah, amazing. Very cool. Very nice. And yeah, what do you like to do for research?
Yeah, so I'm mainly focused in the dynamics of short period planets and multi-planet systems.
Cool.
So, like, um, like transits and RVs are much more sensitive to shorter period planets, and so we have quite a lot of them. And I'm interested when you have lots of planets in the systems, they're all torquing each other, they're all gravitationally affecting one another.
Right.
How um, does that affect their stability and detectability?
Cool. Very cool. Oh, and what is your position there at UCLA? What are you?
I'm currently a PhD candidate, so just a year or two more.
Ooh, awesome. Well, I look forward to calling you Dr. Very good. Pardon. Okay, let's get okay. Good. Well, good. Gonna do have to do a merge there. Okay, let's bring up the article. And here we go. And quite regular. Okay. This is an APJ. It's open access. It's the open access era, people. Go grab a copy for free. Let's sweep. The effect of evolving J2 on the resonant structure of a three-planet system. And Thea, take us away.
Okay, so thanks, Frank. This article is mainly motivated by, of course, as I said before, we've discovered many, many short period planets, though currently the lower bound of the lower bound of the planets we're able to detect is around like one Earth mass and one Earth radius.
Uh-huh.
So we were thinking as detection methods improve, we'll be able to detect smaller and smaller planets. Um, and if those planets are orbiting in, or if those planets are living in systems where we've already discovered planets, that means they're going to be experiencing torques
Yep.
um,
Cool.
from the other planets in the system. And so basically, that's the motivation of this paper. How can we quantify when there's lots of planets in the system, these smaller, lower radius, lower mass planets,
Got
how
it.
do they live?
Right. Very cool.
Um,
Okay.
yeah, so also one like population of planets are the so-called ultra short period planets with periods of like 1 day or fewer.
Okay.
We've discovered actually quite a few, um, though they are intrinsically rare. I think TESS has like 100 such
Okay.
candidates, and so they're really exciting because they orbit so close to the star, and more detections of them, learning more about them, can help us better constrain planet formation models. Um,
Cool.
Maybe help explain the radius gap. So they're
Mm.
really exciting. They're a
Right.
really
Right.
exciting population of planets. And
Cool.
so that's another reason why we wanted to look into them. Though
Mm.
in this paper, we're not limiting ourselves to just ultra short period planets because the dynamics that a orbital period of 23-hour planet and an orbital period of 25-hour planet experience are roughly the same. But we just want to highlight the applicability of these results to ultra short period planets.
Cool. Okay.
Yeah, and more specifically, I've been reading over the past couple of years many papers on the effect of stellar oblateness, so J2,
Ooh,
and
yes.
what effect this has on planets. So just briefly, stars are not rigid bodies, and stars are born with spin. Um, this means that there's a centrifugal force on the surface, which causes the star to be not perfectly spherical.
Yes.
Um, this causes a deviation from the perfect spherically symmetric solution in the gravitational potential, which
Mm.
causes extra precessions in planets, which can maybe do some interesting things. So I've been reading lots of papers by Juliette Becker, Goncia Lee, and many others. Goncia Lee is my co-author, of course.
Cool.
And we were interested specifically in the context of short and ultra short period planets. How does J2 affect them specifically?
Yes.
How does the evolution of this parameter J2? So J2 parameterizes the oblateness of the star. And as the star spins down due to magnetic braking, as it torques up its own stellar wind and its spin slows,
Okay.
how does the evolution of J2 affect the planets in the system?
Right. Very cool. Very cool.
Great.
Okay, I'm with you.
Yeah. So to study this, we use a pretty straightforward model. We're interested in secular effects, which is to say effects that occur on timescales much, much longer than one orbital period.
Yep.
So which is to say we're not currently looking at mean motion resonances in this context.
Okay.
And to first order, the effect of different precessions on the orbital elements of the planets, like the eccentricity and the inclination, is pretty simple to calculate. So if we just scroll right back up to equation 1.
Right.
Sorry, thanks.
Okay.
You can see that the
I don't. Okay.
yeah, we're interested mostly in the eccentricity and inclination of the planets, and these parameters are, these orbital elements are affected by two angles: the longitude of ascending node,
Yes.
and which denoted as big omega, and the longitude of periapse, denoted as in LaTeX \var pi, or we call it pomega because it looks like a little omega with a bar over it. This is equal to the longitude of ascending node plus the argument of periapse. And we use this angle because if you work out the mathematics, the this pomega angle is associated with the eccentricity much more mathematically cleanly than the longitude of periapsis is. But
Right.
it's just the longitude,
Yes.
this longitude of the periapsis, pomega, is just the longitude of ascending node plus the argument of periapsis.
Cool. Okay.
Great.
I'm with you.
And yeah, in equation 1, we just showed to first order how do these parameters affect one another.
Yep.
We need to define a disturbing function. That's in equation 2. But it's all relatively straightforward. You can read about it more in the classic textbook, Murray and Dermott, Solar System Dynamics.
Yay.
Yeah, and so if we scroll down just a little bit more, we can see the we can also quantify the effects that if GR, so general relativity precession, that's in equation 11, that affects the argument of periapsis.
Yes.
That causes precessions, and that will affect the, as we'll see much later in this discussion, that will affect eccentricity. And if we also scroll down, I think just a little bit more to equation 15.
There's J2,
yeah,
Jn, J2.
exactly. Yeah, in equation 15, we can see the effects on pomega and big omega that J2 has on the system.
Yes. Okay.
Yeah. So we have the planets are all torquing one another. We have that calculated to first order. We have the effects of GR and we have effects of J2.
Okay.
And so the main idea of this paper is that when you have 3 or more planets in a system, you can create what are known as secular resonances. Specifically, we'll be looking at first order secular resonances. Okay. This is where the precession in big omega or in pomega of an inner planet, in principle any planet, but for us we're interested in the inner planet of a 3-planet system. That's when the precession of the inner planet is equal to one of the eigenfrequencies of the system, denoted, created by the effects of the other 2 planets. And when this happens, this is known as a secular resonance, and angular momentum transport is greatly enhanced.
Cool. Okay.
And so when this angular momentum transport is greatly enhanced, you can induce a lot of eccentricity onto this inner planet. You can induce a lot of mutual inclination on this inner planet relative to its companions, potentially destabilizing it or making it no longer transit.
There you go. Okay.
So that's kind kind of what we're looking at.
Cool.
And the fun part about J2 is, as I said before, J2 evolves as a function of time. If we look at figure 1,
sure. Let's bring up figure 1.
Oh, sorry, it's up. We already moved past it.
My bad.
No worries. If we look at figure 1, we can see that because of the magnetic braking, because the star is torquing its stellar wind, its spin is decreasing, which means that the centrifugal force on the surface of the star is decreasing, which means that the oblateness and therefore J2 is decreasing.
Right.
So here I show a range of possible evolutions. We know that G stars are born with a range of different rotational periods between 1 and 10 days, I think, and that's what's represented here. The lower bound is a star with a 10-day rotational period, and the upper bound is a star with a 1-day rotational period.
Okay.
And as the star evolves, as it slows down its spin, as its radius changes, the oblateness changes also. And it explores between like 2 to 4 orders of magnitude, this parameter J2, which means that the amount of precession on the longitude of ascending node and the longitude of periapse caused by J2 is going to explore a wide range of values.
Nice. Yeah, one of them was proportional to the square, I thought.
Yeah. So yeah, and if we want to look at the effect of this, we can look at figure 2.
Let's take a look at figure 2 and the secular resonances. Yes, J2 squared. Yep. Or the quantity squared. There we go. Okay, figure 2.
Yeah. If we look at the right column here, the horizontal black lines are the eigenfrequencies I talked about earlier. Sorry, the right column.
Here we go. Oh, sorry. Right column. Here we go. Yes.
Yeah. Those are the eigenfrequencies. And then the
all right.
The x-axis here is the semi-major axis of the inner planet of a 3-planet system. We'll talk about that system's parameters in just a moment.
Okay.
And the 3 different colored lines show the amount of precession in the angle shown on the y-axis for different values of J2.
Okay. Okay.
And intersections, when the inner planet's precession is equal to one of these eigenfrequencies, those correspond to the secular resonances I talked about, where angular momentum transport is greatly enhanced.
Cool. Okay. I'm with you.
Yeah.
We're good.
And so we can see that the effects of, if we froze J2 at one particular value, then there would only be 2 or 1 specific values where these precessions and eigenfrequencies are the same, 1 or 2 specific values of inner planet semi-major axis.
Yes.
But when we allow J2 to vary over time, we can see that the possible semi-major axes of an inner planet, where the possible semi-major axes of an inner planet that will eventually have the inner planet's precession intersect with one of these eigenfrequencies, that range is greatly enhanced when J2 is allowed to vary.
Cool. Okay.
Yeah. And so if we want to look at the effect of this angular momentum transport, we can look at the left column of this figure.
Okay.
So here we have, on the x-axis is also the semi-major axis of the inner planet of a 3-planet system.
Yes.
And in the top panel, we have the predicted maximum inclination induced on this inner planet by its interactions with the other 2 planets in the system. And on the bottom, we have the predicted maximum eccentricity induced on the inner planet by its interactions with the other 2 planets in the system. And we show this for different values of J2.
Including J2 of 0.
Including J2 of 0, which is the dotted line.
Right.
And so we can see that the at around like 0.05 AU, there's this peak, which doesn't, which appears at like J2 is 10 to the negative 4 and never moves. That corresponds to the, I've marked it with a red star. Right, and that corresponds to the right red star on the other panel. And we can see for different values of J2, that intersection doesn't move.
Yes, correct. All curves polar. Yep.
Yep. But we can also see that other peaks are very dependent on J2. And this means that for many different values, potential values of an inner planet semi-major axis, it will be in resonance at one point in time. So if we could pull up the animation real quick.
Sure. Yeah,
Um,
just for clear, we're going to get an animation of the left column here. So I'm going to pull up the animation and play.
yeah, so at very high J2s, for like 10 to the -3, where we start, the precession from
Ah,
the star's oblateness overwhelms, it dominates the precession caused by the interactions between the inner planet and the other two planets. So you don't get any of these peaks at very high J2s near the start of the animation. But
yeah,
as the star's spin slows, as it ages, then this precession decreases, and J2 is not so high that it dominates all other precessions,
yeah.
and the interactions between the inner planet and the outer two planets really come into focus.
Very cool. I like this animation. Nice.
Yes, I like it a lot. So you've probably noticed the variation of the height of the peaks as J2 moves to smaller times.
Uh-huh.
That's not physical. That's just aliasing in the accuracy of this plot.
Ah,
Um,
okay.
the height of the peaks don't actually fluctuate like that. It's just aliasing.
Got it. And we have different colors as we go through. What's the colors?
Yeah, the colors are intended to match the same color scheme as on the
Oh, I
static,
see.
not animated
Yeah,
version
yeah.
of the
Okay.
plot.
Okay.
Yeah,
Got it. Okay.
yeah. So the basic idea is that when you have when you have a static J2,
Mm-hmm.
there's only very precise semi-major axes of the inner planet
Yes.
where its precession equals the one of the eigenfrequencies of the system, and you get in resonance.
Yep.
But when J2 varies for a much wider range of semi-major axis, there will be some value of J2 where it bumps the inner planet's precession just enough to equal one of those eigenfrequencies and enter resonance.
Awesome.
Yeah, we can see that for this particular system, um, like a range between like 0.05 all the way down to 0 semi-major axis. In its
Mhm.
semi-major axis, you get these resonances. So that's really cool. And that, however, it does pose a problem for the potential detectability and stability of this system
Oh,
if it's if at some point during the planet's life it gets boosted up to a 15-degree mutual inclination with its companions,
right.
or an eccentricity of 0.3.
Okay. Very cool. All right. We'll go here and we will go back to the article. And here we go. And there's our static figure. And you can imagine these were all bumping along there. Mm-hmm.
Yeah.
Cool. Okay.
Okay. So
That's
yeah, so let's talk about what system is actually being shown here. So the parameters of this that were used to create this plot were based off of a real system, um, system HD 106315, which is a two-planet system with two warm Neptunes,
okay.
first discovered by K2, and then followed up. Its parameters were first published by Rodriguez et al. 2017, and then I think it's below. And then the masses of the two warm Neptunes were found
There we go.
with RVs, with the HARPS instrument in Barros et al. 2017. And it's actually one of the few systems that has measured stellar obliquities. So the angle between the angle between the angular momenta of the two coplanar warm Neptunes and the star's spin axis.
Yes.
And that was measured by Zhou et al. 2018 with Doppler tomography.
Nice. Okay.
And so I said the parameters we used for figure 2 were based on this system. For that figure, though we'll explore the real system later on,
Okay.
for this figure, we're neglecting the obliquities, so we'll explore them later. And this system is observed to have pretty high eccentricities for its two observed planets. Eccentricities of about 0.2. And so just to for the purpose of making this plot a little bit more applicable to a wider variety of systems, just to start with, we've explored a variation of this system with much smaller observed planet eccentricities.
Okay.
Okay.
Yeah, coffee sounds good.
Yeah.
Okay.
Yes.
I'm with you.
This system is a 2-planet system. There are 2 observed planets, and what we've done is we've said, for the purpose of a nice example, we've introduced a hypothetical inner planet. So, to my knowledge, there isn't an actual candidate inner planet for the system. There is potentially a candidate much further orbiting planet, but we don't include that in this. But we're just looking at this system. We're hypothesizing, for the purposes of education, what would happen to an inner planet orbiting inside the 2 observed planets. And we see that many exciting things can happen to this planet, as we show in Figure 2.
That's part of it.
Yeah.
Okay, good.
And so the inner planet, we give a mass of 1 Earth mass, which is much smaller than its 2 observed companion planet masses, which are like 12 and 15 Earth masses. Okay.
Quite the range there on E.
Yeah, and so what we do to sort of explore what would happen to a potential inner planet in this system is we run a Monte Carlo where we introduce many different 1 Earth mass inner planets at various AUs with various initial eccentricities, with various initial inclinations, and with various initial longitude of ascending nodes.
Okay, cool. Good.
Yeah, and we want to explore is under what conditions is such an inner planet stable? Under what conditions is an inner planet stable but not detectable because maybe its inclination is increased so much that it no longer transits?
Yeah.
Of course, it still could be picked up by RVs. With the main idea being there's many 2-planet systems, and we're interested in when can an observed 2-planet system potentially host a currently too small to be detected inner planet, and maybe more importantly, when could it not? When can we say, oh, there's plenty of room in semi-major axis to put an inner planet here, but we can say via dynamical arguments that if there was indeed one there, it would have been destabilized long ago, or it would be too inclined to detect via transit.
Okay, nice.
Okay.
A way of getting at the small bodies. It's like a telescope.
Yeah.
Okay. Yeah, we'll come back to that point there in a bit. Okay.
Yeah. So this section in the paper is just describing this proof of concept system where we augment the real parameters of HD 106.315 and we introduce our hypothetical inner planet.
Yes.
Yes, and if we scroll down to the next figure, we can. Oh, sorry.
Figure 3.
Let's skip to Figure 4 and come back to Figure 3.
All good. Figure 4.
Okay. So yeah. So we took HD 106.315. We simplified its parameters a bit, reduced the obliquities, reduced the eccentricities of the 2 observed planets, and then introduced hypothetical inner planets at a variety of different semi-major axes, eccentricities, and inclinations.
Okay.
And the result of that is this 6-panel plot. So let's go sort of step by step. I showed in Figure 1 that the initial spin of G and F stars is quite variable between 1 and 10 days. So we wanted to run our Monte Carlo experiments with 2 different initial spins. And we do that in the left and the right column here. So the left column has a small initial J2, and the right column is a high initial J2. And I think this plot pretty cleanly demonstrates what effect that can have.
Yeah.
And so then the plot is divided into 3 rows. The top row is this parameter called delta, which the precise definition is shown in the paper, but basically delta equals 0. Yeah, I think it's, sorry, you have to scroll so much.
Okay.
Yeah, equation 17.
All good.
Delta equals 0 when the apoapsis of the inner planet is further away from the star than the periapsis of the middle planet, which is a heuristic. When delta equals 0, that means orbits approximately cross, which is our heuristic to say the system is unstable.
Okay. Okay.
Yeah. So that's and if we go back to that figure, we can see that delta is non-zero for much of the semi-major axis range in this, which is good because when delta equals 0, the system is unstable. I've shaded the regions on the right where delta equals 0 with orange to indicate instability.
Okay. Okay.
And also the shaded region on the left is the Roche limit of the star, where if a planet were there, it would be disrupted.
Okay. Or spiral in or do something.
Yeah.
Okay. Good. In the green and
So the
purple dots.
yes, there's lots of stuff to talk about. Yeah. So the blue dots, excuse me, the blue dots correspond to straightforward integrations of the equations. I think it was equation 1, way up at the top, that just show, yes, equation 1, that just show how the eccentricity and inclination of the all of the planets in the system will evolve to first order. Of course, real life is not just first order, so the green stars correspond to n-body simulations using the Mercury 6 integrator.
Nice. Okay, very cool.
We can see that there's pretty good agreement basically everywhere between the blue dots and the red stars, which is an indication that this approach is indeed accurate, which is very good to see.
Nice. Okay.
Yeah. And so if we look at the if we look at the middle row, that's the maximum eccentricity induced on the inner planet by its interactions with the outer two planets over the entire 2 gigayear integration.
Okay.
And if we look at the right-hand column, we can see that there's this big plateau between 0.02 and 0.05 AU of greatly increased eccentricity. And then after 0.05 AU, it drops off to like 0.2 as opposed to 0.4. And the reason it drops off is because there are no resonances further away than 0.05 AU, and the resonances are indeed driving this eccentricity increase.
All right, cool. I'm with you.
All right, and then if we look just below, so the bottom right panel.
Max mutual inclination.
Yeah, this is the maximum mutual inclination induced on the inner planet, between the inner planet and its companion planets throughout the course of the integration. And the 2 companion planets, the 2 warm Neptunes, remain coplanar for basically all time, which is great and consistent with reality because indeed both of them transit, so they should be roughly coplanar. There's some caveats to that, of course. And then the red line on here is the barrier between always transiting and not always transiting. So all points below the red line always transit. They don't have enough mutual inclination with the other 2 planets to no longer transit. And points above the red line, there are scenarios, particular orientations, where with that mutual inclination, it can escape and avoid transiting. Yeah, and because both of the companion planets, the outer 2 planets in the system, do transit, this is an important distinction to make if we want to be concerned with, because we are concerned with the detectability of this hypothetical planet.
Very good. Okay.
Yeah, and we can see that in the in this right column where we have high J2, we have these great regions of excited eccentricity and excited mutual inclination. The one might notice that the maximum inclination drops at very, very small semi-major axes.
Yes.
But the maximum eccentricity drops much earlier at like 0.2 and shorter. That's because of general relativistic interactions. The GR precession on the longitude, or sorry, the argument of periapsis, when the inner planet orbits close enough to the star, this GR precession dominates the precession of the argument of periapsis, which prevents these secular resonances from actually occurring. So in the previous plot and in the animation that was without GR, we can see that when we include GR, things are very consistent with the plot and the previous plot and the animation. But however, the low semi-major axis eccentricity is suppressed.
Yes.
Okay.
OGR. Okay.
Yes, exciting.
Okay.
All right. And I love to spend lots of time getting to talk about my plots. If we look at the left column, so this is with a lower initial J2, we could see that there are some significant differences between that and the high initial J2.
Uh-huh. Mm-hmm.
We can see that at moderate moderate semi-major axes between like 0.03 and 0.04, the amount of mutual inclination induced on the inner planet and the amount of eccentricity induced on the inner planet compared to the high initial J2 case is much reduced.
Yes. Yes.
And the reason why this is because the resonances that would excite eccentricity and mutual inclination on these planets with moderate semi-major axes, those resonances occur at J2s higher than 2 × 10⁻⁵, which is the initial J2. So such planets never experience these resonances because J2 started out too low for them to be experienced.
Sure. Sure.
Yeah, so this means that the initial spin of the star is actually somewhat significant. And for this hypothetical system, there are like if for this hypothetical system, a planet orbiting at like 0.03 AU would only be reliably 100% detectable via transit if the initial spin of the star was lower.
Yes. Yes. Okay.
Okay. So these are plots of the maximum eccentricity and the maximum mutual inclination as a function of time, but as a function of semi-major axis. But it's also important to consider what the actual eccentricity and inclination as functions of time looks like. So if we scroll up to figure 3.
Okay. Figure 3 time dependencies here. Okay.
Yeah. We can see the effect of these resonances that sweep across the semi-major axis field. So this is one of the simulations shown in the Monte Carlo in figure 4, where the semi-major axis of the inner planet is at 0.021 AU.
Okay. Okay.
And we can see that the effect of the resonances that move across the semi-major axis range is to permanently increase mutual inclination between the inner planet and its companion planets. So the color scheme here is on the top left panel. This is the mutual inclination for the 3 planets. It's the mutual inclination between the planets indicated by the legend and
Nice. Okay.
the middle planet. So if you see on the top left panel, the mutual inclination between planet B, the inner planet, and planet B, the inner planet, is always going to be 0, of course. And we can also see the mutual inclination between the outer planet, planet C, and the inner planet between the middle of the planet. And we can see that the effect of these resonances, this exchange of angular momentum, aligns the outer planet and the middle planet, because the mutual inclination in blue for the outer planet goes to 0. That's a mutual inclination between the outer planet and the middle planet. So they align themselves together.
Yes.
And by law of conservation of angular momentum, the inner planet becomes greatly misaligned from the other 2.
Okay. Very nice.
Yes, it is exciting. And you can see in the bottom 2 panels, like the how the angles of the longitude of ascending node and the longitude of the periapsis are affected by this.
You have a couple
And
of gaps there in the bottom ones, right?
yeah, exactly, indicating that there is indeed a resonance going on, controlling what angles are allowed.
Yep. Okay. Just wanted to call that out.
Yeah, thank you. Yeah, and so we can see on the top right panel, a very similar thing happens to the eccentricity, though it happens at a much later time.
Yes.
Angular momentum is permanently exchanged between the inner planet and the outer two planets, increasing the inner planet's eccentricity and reducing the eccentricities of the other two planets.
Mhm.
Yeah. And so the important thing to take away from this is that indeed the maximum mutual inclination between the inner planet and the companion planets is increased, but also that the variation about that maximum mutual inclination is very small. Like the mutual inclination between the inner planet and the outer planets varies between like 16 degrees and 13 degrees, rather than, for example, 16 degrees and 0 degrees, which would create many more situations where the system would be detectable. Here, since that variation is so small, it's permanently misaligned and it doesn't come back into alignment.
Okay.
Yeah. So that is, yes, this plot I like very much. It's very exciting. It cleanly shows these misalignments are taking place.
Beautiful. Beautiful. Okay.
Okay. So I think let's look at the next figure. So not figure 4, but let's actually look at figure 6.
Okay, down to 6, and here we go. Now this is the real system, HD 160315. Okay.
Exactly right. So in figure 4, we looked at a modified version of HD 106315, but here this is the real system with stellar obliquity, the 10-degree stellar obliquity included, and the outer planet's eccentricities included.
Okay.
And we can see that the story is a little bit more complicated for the real system. The eccentricities and the stellar obliquity has affected the evolution of the system by quite a lot. Most dramatically, the eccentricity induced on the inner planet is greatly increased. You'll notice that the amount of green stars has been reduced. This is because in this middle row, systems that become unstable, I've just put them at eccentricities of 1, and I've made their stars teal.
Yeah, they've gone away. Okay.
Yeah. Similarly, because the inner planet has scattered off of the outer planets, those stars don't appear in the bottom graph because the inner planet has either collided with the star, with another planet, or been ejected.
There we go. Okay.
Okay. So it doesn't look very good for detectability in the terms of the maximum mutual inclination for this system. The resonances cause huge amounts of mutual inclination. This is driven by, in part, the significant obliquity, the angle between the outer companion's angular momentum and the star's spin axis.
Yes.
So lots of the inner planets, even if they are stable, would be very, very hard to detect because they have such great mutual inclination, but they're often just unstable. We can see that this orange region, the region where delta equals 0, is much, much larger than in figure 4. The system is greatly unstable, huge amounts of eccentricity induced on it, and very, very few places where the planet is stable and possible to detect.
Right. Ooh, reality is always such a little messier. Okay.
Yeah. Such a shame. Though this system does have like significant eccentricities in the outer planets, which you're not going to find in every system.
I'll save that for a future question. Okay. Cool.
Okay. Yeah. And so, yeah, let's scroll back up and look at figure 5.
Yeah. Yep.
Yeah, this is just a way to quantify what are the parameters in the system that are controlling how much mutual inclination you get and how much eccentricity you get. So in the top panel, we have the x and the y axes are the mutual inclinations between the outer planet and the inner planet, and the middle planet and the inner planet, respectively. And the color scheme here is the maximum mutual inclination induced between the inner planet and its companions. More yellow is more mutual inclination. And it's
yes.
Yeah. And the bottom panel is a very similar story. On the x and y axes, we have the eccentricities of the outer and middle planet, respectively, and the color is the inner planet maximum eccentricity.
Too close. Okay. How about the black dotted lines in the upper one? What do those signify?
Yeah. So
Blow that up.
Yeah, that's good. The outer planets are observed to both transit, so their inclinations cannot be too different. So that black dotted line indicates the region where both of the outer planets both transit forever.
Okay.
Hence, outer planets co-transit boundary.
Got it. Got it.
And then the white lines are each for a particular semi-major axis of the inner planet. Those are the regions where the inner planet stays detectable, stays co-transiting with its two companions.
Okay.
Yeah, and we can intuit from the shape of the dotted black line that it's the mutual inclination between actually the middle planet and the outer planet that matters. We see that in this sort of y equals x strip in the middle, the inner planet mutual inclination between the inner planet and the companion planets is much, much smaller than when one of the companion planets has a inclination of 0 and the other one has an inclination of 15.
Oh, yeah.
Yeah, so when the companion planets are aligned, the amount of mutual inclination induced on the inner planet is smaller than when the companion planets are greatly misaligned from one another.
Awesome. I'm with you.
Yeah.
Very nice. Okay. Very cool.
Yeah.
So that was that one. We did 6.
Yeah.
There's a nice little appendix on this one.
Pardon?
There's a nice little appendix on this article as well.
Yeah. This appendix is comparing the in the figures 4 and 6, we have these blue dots, which is the secular code that I wrote, and also the green stars, which corresponds to n-body. And we're interested in just demonstrating that they agree on the behavior of these systems. We can see that the n-body code in this figure has wider variations about the mean eccentricities and inclinations, but that if we look at the y scale, the y scales are pretty zoomed in. The n-body code and the secular code agree quite well on what the average eccentricity and what the average mutual inclination is. That's that's what this appendix says.
Always a good verification. Very nice.
Yeah.
Very nice.
All right, and those are the big takeaways of the paper. We made it.
You made it. Awesome. Thea, thank you so much for walking us through your very lovely APJ article.
Thank you very much. And also, of course, thank you very much to my co-authors. Smita Nawaz is my advisor here at UCLA. Quincy Lee is a collaborator. And Nicholas Nzunza is an undergraduate I've been working with.
Awesome. Very nice. Very nice. And you touched on it a little bit as you went through there. And so I'll ask you to extrapolate here a little bit.
Okay.
So where do you think we go with this topic, let's say over the next couple of years? Are there additional systems that one can try this out on real systems? Are there theoretical improvements that could be done? So, for example, maybe tidal interactions, something along those lines. And just sort of next steps, where do we go with this?
Yeah, so in this paper, we looked at a hypothetical inner planet for an observed system. Of course, 3-planet systems do exist. We have seen them. So actually, what I'm working on right now, and what I'm hoping to get on the archive, ideally by the new year, if everything goes well, is an exploration of observed 3-planet systems. How many of them are in secular resonance? How many of them have J2? How many of them do we expect J2 variations to cause significant effects? Yeah, and this is mostly for FG and K stars. So right now I'm looking at 36 such observed systems, and I'm looking forward to am currently characterizing the effect to which secular resonances and J2's effect on secular resonances can affect the stability and detectability of these systems.
Nice. Very cool. Well, I look forward to seeing that work come out.
Thank you very much.
Nice. APJ, of course.
Of course, always.
Very good. Thea, I want to thank you so much for walking us through your very lovely article. Thanks.
Thanks for inviting me.
And that will do, everyone. And I hope this made your astronomy day resonant a little bit better. And we will see you on the next one. Bye-bye.